Hi everybody. Just thought I would give you a brief rundown of Quine McClusky method. What we're going to do here is we're going to take the given function of the canonical sum of products form using min terms 4, 5, 6, 8, 9, and 10. First thing I'm going to do is write out radix equal 10 and write out my min terms 4, 5, 6, 8, 9, 10, and 13. I'm going to write them out with radix equal 2 using 4 bits. And then what I'm going to do is I'm going to come out with the Hamming weight. And that'll be equal to the number of ones in each one of the bit vectors. Now what I need to do is I need to order the min terms in terms of their Hamming weight. And we're going to call this column 1. So first group in column 1 will be those elements which have a single bit. Next group in column 1 will be those elements with 2 bits. Next group in column 1 will be those elements with 3 bits. And I check things off as I go so I don't miss anything. And then we start with what's called column 2. Now in column 2 what we're going to do is we're going to match. And if there's only one bit of difference between two min terms, we write down the min term with the bit that's different with a dash. So this min term matched with that min term, and now the two min terms have been covered. And this represents a loop in the K-map, which we're going to grow. We can compare this min term against the next min term, and we'll get 0, 1, dash 0. Now we can compare it against here, but there's 2 bits of difference, so it doesn't work. Compare it against here, 2 bits of difference, doesn't work. Go to the next one, compare it against here, 2 bits of difference, 2 bits of difference. Now we see 1 bit of difference in the least significant bit, and that makes 1, 0, 0 dash. And we do it again here, and that makes 1, 0, dash 0. And now we can compare these min terms against the final min term, and that'll make dash 1, 0, 1. Has 2 bits of difference here, so that doesn't work. Here's 1 bit of difference, so that's 1, dash 0, 1. That's from here to here. And then we can go from here to here. We see 2 bits of difference. Well, now let's see. Didn't we get coverage here? Yeah, we did, so that got covered. So every implicant in column 1 has been covered, and now we're going to column 3. And now what we're seeking to do when we do our match is a match with the dashes, and the dashes don't seem to match with anything here. The dashes don't match with anything there. Dashes don't match with anything here. And the dashes don't match with anything there. So now we have essentially reduced ourselves down to just these remaining terms. And if you want to, you can identify what the terms are. This is 1, 0, 0, 0, which would be 4, or 1, 0, 0, 1, which would be 5. So 4 and 5 are covered here. 0, 1, 0, 0, that's 4. And or 0, 1, 1, 0, and that would be 6. We've got 1, 0, 0, 0, that would be 8. 1, 0, 0, 1, that would be 9. We've got 1, 0, 0, 0, that's 8. We've got 1, 0, 1, 0, and that would be 10. Here we have 0, 1, 0, 1, that would be 5. 1, 1, 0, 1, that would be 13. Here's 1, 0, 0, 1, that would be 9. 1, 1, 0, 1, that would be 13. So at this point now, we've got the ability to do what they call the prime implicant chart. And we'll just write that out. So that's a chart, right? As opposed to the implication table, which you might have seen in your state reduction diagrams. And so at this point, we've got let's see, 4, 5, 6, 8, 9, 10, and 13. 4, 5, 6, 8, 9, 10, and 13. And we can write those across the top. Of our initial prime implicant chart. And then across on the left, we'll write, let's see now, 0, 1, 0 dash, which corresponds to 4 and 5. 0, 1 dash 0, which corresponds to 4 and 6. 1, 0, 0 dash, which corresponds to 8 and 9. 1, 0 dash 0, which corresponds to 8 and 10. Dash 1, 0, 1, which corresponds to 5 and 13. And finally, we've got 1 dash 0, 1, corresponding to 9 and 13. And it looks like there's a little blemish in my video because I was unable to capture the lower half of the screen. Let's see what we can do about that. There we are. Much better. So now, now you can see how we've set up the table. Basically, I copied from up in here down to over here. And what we're going to do is we're going to put an X in 4 and 5, an X in 4 and 6, an X in 8 and 9, an X in 8 and 10, an X in 5 and 13, an X in 9 and 13. If you have something that's all by itself in a column, then it becomes an essential prime implicant. So that's here. That's an essential prime implicant. And what you do is you say you're going to have coverage through here. And as a result, you'll also have coverage here. If you see another column all by itself, for example, right in here, that's another essential prime implicant. So you get coverage in through this space, you get coverage of that space. And so now you're looking for implicants that can be maximized in terms of the total number of columns, something that gives you coverage over the maximum. So if you decide to use this one, you'll get coverage here and there, but you'll be missing there. If you decide to do this one, you'll get coverage here and here, but you're going to have you'll be missing there. So in effect, you're trying to minimize the number of loops that you need. Can't really see any good way to reduce it any further, so what we'll do is we'll cover here. There's more than one way to loop these things. And that'll give us coverage there. And then we'll have to go with one more loop. So in effect, what you're going to need is this loop, that loop, this loop, and that loop. And if you look at the pattern that this creates, that's A prime, B, let's write it out, A, B, C, D. So we leave out the C because there's a dash. If A is a 0, we write A prime. If B is a 1, we write B. Since D is a 0, we write D prime. So this corresponds to A prime, B, D prime. And this corresponds to A, B prime, D prime. And this corresponds to B, C prime, D. And this corresponds to A, C prime, D. And now you've got your minimum sum of products form. And you can write it out as F equals A prime B D prime. That's this first term. Next term plus A B D with primes on the last two, plus B C D with the prime in the middle, plus A C D with the prime in the middle. And that looks like a minimal sum of products form. Now, for your verification, let's do a K-map. Right, always number your K-maps, always label your K-maps. Let's take a look at the min terms. We know it's going to be 4, 5, 6, 8, 9, 10, and 13, with all the rest being 0. Let's see, where can we do our loop? Looks to me like we can loop here. Now is going to correspond to A, B prime, and D prime. And this is going to correspond to A prime, B, D prime. And then the looping in the center, this is the one where things can get a little bit arbitrary. We'll do A, C prime, D. And then over in here, we'll get something like B, C prime, D. So let's compare our result. We've got F equals, and we can write out A prime, B, D prime, and that checks. We can write out A, B, D prime, and that checks. A, B prime, D prime. We can write out BCD, BC prime, D prime, and that checks. And finally, we can write out AC prime D, and that checks. So now we have validated the Quine McClusky method against the K-map. Hope you liked my little presentation. That is as about as complicated a Quine McClusky algorithm as I would attempt by hand. Thank you.